So maybe it would be more like JD.
Okay, let's get started. All right, so today we're going to really focus on policy gradient. So we're going to start by just recapping what we did with policy gradient. And then we will go from there to figure out why it's hard, specifically issues around variance. And then we'll talk a little bit about how to fix some of those issues. And then move on to something called the natural policy gradient. Cool. How much do people remember about policy gradient? A lot? A little bit? Should we go over it from the start? Yes? Yes? Okay. Cool. So where we are is we have a lot to cover. So we're at policy gradient right now. And then the end will go super fast. But we're going to spend today and Monday on policy gradient. And then we will do paper discussions next Wednesday. Most of you who are presenting should have gotten an email, or everyone who's presenting should have gotten an email from me. And your name should be on EdStem. And if you see your names on EdStem and no email from me, let me know. But it's just try reading the papers before you come in. Otherwise, it won't be as productive of a class for you. Okay, good. So the objective for reinforcement learning is maximizing the expected sum of rewards under your policy and your system dynamics, right? And so everything we want to do is to maximize this objective. Now, how are we going to maximize this objective? We can either do it with gradient descent, we can do it with dynamic programming, or we can do it with model-based optimization. We started by thinking about gradient descent, right? And so all of the end of last class was about trying to instantiate what gradient descent looks like for that objective, right? And so we said that, hey, gradient descent is if you have an objective, let's call it J theta. You want to just do ascent by moving in the direction of the gradient, take little steps in the direction of the gradient. And so you want to start from some theta naught and continue to take little steps with some step size alpha till you reach some local optimum, right? And so we said that gradient descent is going to be the steepest ascent in the Euclidean norm, which we'll talk about. Hopefully, we'll talk about it at the end of this class. But like intuitively, you can kind of think of it as the ascent, like the gradient tells you the direction in which the objective is maximized, and you take little steps in that direction because the gradient is like only a linear approximation, right? So you have to take linear approximation, take a little step, recompute, take a little step, recompute, take a little step, right? So that's what gradient descent is doing. Okay. So we talked about gradient descent, and then we said, hey, like we want to apply gradient descent to this objective. Right? So this objective, which is the expected sum of rewards. Now, what makes this objective hard to do gradient descent on? Or not obvious? Why is it not just supervised learning? That's right. And so you have an objective where the distribution that you're taking the expectation with respect to depends on theta, as opposed to supervised learning, where the thing inside the expectation depends on theta, but the data distribution itself does not depend on theta, right? And so you can kind of think of this as you don't have control over the data distribution, you just have control over the function inside, kind of like with supervised learning. And that is you have control over the data distribution, but you don't have control over the function inside. So it's like f of x is like your reward. You can't control the reward. You can just control what states you get to get that reward, right? And so then the goal is to move your p theta towards areas where you get as high reward as possible. And so you're controlling the thing that you're taking expectation with respect to and not the thing inside, right? So the supervised learning objective, we could just move the theta inside the expectation. So gradient of expectation is expectation of gradient. It's simple because we had the derivation last time where we just move this theta inside or move this gradient inside. And so you can show that the thing on the bottom is essentially the expectation, x coming from g of x of the gradient of f theta of x, right? So gradient of expectation is expectation of gradient, which is because the expectation term does not depend on theta, right? Now, if we think about this term, we can't really move it directly inside because this term depends on theta. So that's what makes it hard. That's why we need all of this extra machinery. Okay, everyone with me so far? So the difference here is you can move the gradient inside here, you cannot move the gradient inside there. And so that's kind of what we covered last time. Okay, so before before I actually recap the math, does anyone remember how we did it? How do we deal with this expectation with a variable that depends on theta? How do we deal with that? Yeah.
We divided by the thing over itself.
That's right. Okay. Yeah. So let's start from the top. That's essentially the trick. So we have this objective. Let's call it j theta. For now, we're going to do it in terms of trajectories. We said it's the expected sum of rewards. R is the sum of rewards in a trajectory. P theta tau is the likelihood of a trajectory, right? And we said the expectation is essentially the integral P theta tau R tau d tau, right? And then we said, okay, we want to take the gradient of this thing. So you're going to take the gradient of this thing. You can move the gradient inside. And this is the only term that depends on theta, right? And so what you get, oh no. What you get is the gradient moves inside. The gradient hits this. The problem with this is that it's not an expectation, right? And it's an integral. Integrals are bad, expectations are good. So we want to reconvert this into an expectation. And so we did this trick of multiplying and dividing by p theta, right? And then we grouped these terms together, right? And so you can kind of think of this as this is the probability. This whole thing is your function, and it looks like an expectation again, right? So we just multiplied and divided and like rearranged the terms a little bit. So we wrote this as p of p theta of tau times grad theta p theta of tau divided by p theta of tau times r tau d tau, right? And this starts to look like an expectation again. So we're happy. Okay, so we multiplied and divided, just regroup the terms. And then we use the fact that the gradient of the log is, 1 over x dx d theta. And we use that to kind of reconvert this term grad p over p, like this term over here. You can write it as essentially grad theta log p theta tau, right? Just using the chain rule. So all we did to get here was we multiplied and divided by p theta, regrouped the terms, and used the chain rule. And so this gives us essentially a much simpler looking expression, nothing in the denominator. You never want to divide by probabilities. That's bad because it'll blows up if the probabilities are too small. So try to never have probabilities in your denominator. Bad. So this now looks like an expectation. It's the expectation of grad log p theta tau times r tau with respect to p theta tau, right? So intuitively, you can kind of think of this as I'm going to take samples of trajectories from my trajectory distribution p theta tau, right? And then for each of them, I'm going to compute grad log p theta tau multiplied by r tau and take the average to get the gradient, right? And so intuitively, the easiest way to think of this intuitively is you're going to sample a bunch of trajectories, and then you're going to increase the likelihood of those trajectories proportional to the reward of each of those trajectories. So it's like whichever trajectories are higher reward, you will increase the likelihood of those occurring. Whichever trajectories are lower reward, you'll decrease the likelihood. And so essentially, this objective is just codifying trial and error. It's saying, let me try a bunch of stuff. Let me figure out what the reward was for each of the things that I tried. And then let me increase the likelihood of the things that were better. Right? And so that's all this objective really is. Yeah.
So even if our trajectory has some bad actions, but if the end reward is good, that doesn't still get.
Yeah, that's a great point. So,
but statistically over time.
So that's going to be the issue with policy again. It's going to be basically what happens is you lump everything together. And so it's like, okay, it's even worse if you have some good actions and you led to a bad outcome. And so what happens is good actions when you lump with a bad outcome will be weighted low, and then you push them down, even though they're really good actions, right? And okay, when you cover all possible actions, when this thing covers everything, then it works out fine. But you're doing it with samples, right? And so that's what results in this variance problem, or the word that people often use for it is credit assignment. It's like if you have a combination of k steps, there might be some good things lumped with some bad things, and they'll all get lumped together. So that's what causes the variance problem. Okay. Everyone with me on this derivation? Sometimes you can, sometimes you cannot, right? Like sometimes you have to take 100 steps to solve a problem, right? Or take 10,000 steps to solve a problem. Sometimes you have to Like you're playing StarCraft or something, you have to take some number of steps. And so you can't really shorten the horizon. What some people often do is that they like use something they call reward shaping. And what reward shaping lets you do is it makes that reward really informative so that even if you solve like a wrong short horizon problem, the solution is the same as a longer horizon problem. So it's kind of like, imagine I was solving a maze. One of the objectives I could do, one of the rewards I could give is like +1 at the end of the maze and 0 otherwise, right? And then I have to solve the long horizon problem. The other reward I could give is like a dense reward, which is like distance to the goal, like a very informative reward, which is distance to the goal, right? So like, imagine I was in this maze, and this is my start, this is my goal. One of them is like +1, 0 here, right? And there I have to like solve this long horizon problem to even see the reward. But if I like had a denser reward, what I could say is that, okay, I'm going to like, for each point, I'm going to assign a reward which is equal to the distance to goal. Then I can shorten the horizon and still solve the problem optimally, right? And so that's often in the process of algorithm design that you design the reward, which shortens the horizon. So a lot of the tricks to getting policy grid to work is effectively shortening the horizon. But sometimes you can't. Okay, does that make sense? Yeah.
Why is it wrong to take gradient of expectation? Like, let's say I don't do this trick. Why would we have to derive it?
So, okay, so if you remember what we did last time, we did expectation of x coming from g of x, f theta of x, right? And we said, okay, we're going to take the gradient here. And the reason we could move the gradient inside, right, was because if you write this as an integral, this is g of x, f theta of x dx, the gradient, right? And this gradient goes back inside. And so now you can write this as integral g of x grad f theta of x dx, right? Which you can convert back into an expectation, which is essentially the expectation g of x of grad f theta, right? That's what we did last time. And so there you could essentially move the gradient inside because the g did not depend on k.
The question is actually, why do you want to move the gradient? Like, why can't you leave it? Like,
because you need to find a tractable way to compute the gradient, right?
okay.
Like an expectation is just an average of a bunch of things, right? And so you need to find a computationally tractable way to compute a gradient. As in, if I just look at gradient j theta, it's like an abstract term. Like I need to find a way to like implement it in code, right? And so, for instance, that thing is implementable in code because I take each f theta, I take the gradient and I average all the gradients, computable in code. If I look at this objective, I don't know how to compute it in code because I need to like, a gradient is like, you have to like, you can compute it with finite difference or something, but if I want it analytically, I like don't know how to compute this analytically. Now, when you convert into this form, you do know how to compute it analytically because you can compute grad log p, you can compute r, and then you sample a bunch and take the average, right? So it like, makes it computationally tractable. So the important part is we need to go from the abstract term to something we can compute in code. Okay, so the reason expectations are good is for what I just told Sid is because you can implement them by just doing sampling, right? So whenever you have expectations, you can approximate them by just taking a bunch of samples and averaging them. It's like this is what you call a Monte Carlo approximation. But if you have an integral, then you're like always going to get a wrong estimate unless you like integrate over all of the things, right? And so that's why you want to try and convert every expression into an expectation. Okay, so this thing that I have here is still not expressible in code. Like, what is p theta tau, right? We don't know what p theta tau is. So the next thing we're going to do is we're going to try and make this even more concrete, right? And so we're going to try and define what p theta tau is, take the gradient, and then try to get into something that we can like implement in our homework, right? So to remind everyone what p theta tau is, it's the likelihood of a trajectory, where a trajectory here is going to be a sequence of states, actions, states, actions, states, actions, right? So trajectory is the likelihood of, there's some here. It's a trajectory is a sequence of states, actions, states, actions, states, actions. I'm not including reward here because we're assuming reward is deterministic. But if rewards were not deterministic, you would also sample rewards. Yeah? So I'm going to assume rewards are deterministic functions of state. But the likelihood of a trajectory, you can think of it as, if you remember my first lecture, we talked about how we do sampling, right? So we start by doing like sampling of the initial state, then you sample the next state, then you sample the first state, then you sample an action, then you sample the next state, then an action, then the next state, and you repeat, right? So you can think of like the likelihood of a trajectory as the likelihood of the initial state, P of S naught, times the likelihood of the initial action, times the likelihood of the next state, given that initial state and initial action, times the likelihood of the next action, times the likelihood of the next state, repeating, right? So you can think of this as, this is how likely it was that I got the initial state. Given that initial state, this is how likely I got the next act or the first action. Given those two, this is how likely I went to the next state, right? And so using the Markov property, you can kind of write the likelihood of a trajectory as the product of an initial state likelihood times the dynamics likelihood times the policy likelihood, right? Does that make sense? Question? So try to think of it as like a chain, right? So it's a chain where things are independent from each other, right? So like the likelihood of S1 only depends on A naught and S naught. The likelihood of A1 only depends on S1. The likelihood of S2 only depends on S1 and A1. The likelihood of A2 only depends on S2, right? And so that's why you can write it as this chain of initial state times dynamics times policy times dynamics times policy times dynamics times policy, right? Till the end of the chain. Yes? Everyone seems a bit confused. Questions? Basically, if I have a distribution of random variables, right? If I have a distribution of random variables x1, x2, x3 in a chain, I have x1 going to x2, going to x3. I can write the likelihood of that chain as P of x1 times P of x2 given x1 times P of x3 given x2, right? You're like splitting up your chain. That's what the Markov property is. And so it's basically the same thing with just actions in the mix. Like this thing is just that thing with actions. So it's an initial state times the policy times the dynamics times the policy of the next step times the dynamic. Repeat, repeat, repeat. Till the end of your chain, right? Okay. Yes? Okay, good. So if we do that, that's the definition of the likelihood of our trajectory. We want to stick that back into our objective, the expected grad log P times R. Log P is going to be log of the initial plus log of the dynamics plus log of the policy, right? It's just like log of a bunch of log of the product of a bunch of terms is the sum of the log of each of the terms. And so the nice part about this is when I take the gradient, I can decompose the gradient into the sum of the gradient of the individual terms. And then I'll notice that only one of the terms actually depends on theta. Right? So only the last term depends on theta. And so these terms go away. It's a gradient of a constant, essentially. Right? And so these terms go away, hence you're model free, right? Because this is your dynamics model. When you say model, this is what you think of as your model. Your gradient of your model goes away. So you never need to know your model. You just need to be able to sample from it. And so the nice part now is grad log P theta tau is the sum of grad log pi theta. Okay. Now this is computable because I define what pi theta is. Like pi theta is a Gaussian policy. If you remember imitation learning, it's a Gaussian policy or a mixture of Gaussian policies or an autoregressive policy. Like I define pi theta. It's like something I've coded up in PyTorch. And so I can compute the gradients. And so I exactly know what the gradients of log pi theta are. Right? And we'll cover a concrete instantiation in a second. But this is like fully computable by me. I don't need to get anything from the environment except for what the states and actions are. And I don't need to like get the gradient of the environment at any point, just the gradient of my policy. Okay. So although policy gradient is called like, it's a gradient-based method, it's actually not taking gradients through the environment and it's not taking gradients through the objective. It's only taking gradients through your policy. So unlike like when you have like an objective, like we have an objective like a non-convex function or something, right? And you're like doing gradient descent on it. You're kind of like following the gradient. You're taking a gradient through the function. In policy gradient, the name is a little bit misleading because really what you're doing in some sense is you're trying out a bunch of stuff. You're sampling, no gradients, and then you figure out which of the stuff works best, and then you're not taking a gradient through the environment or through the reward. You're only taking a gradient to move your policy parameters in the direction that makes the good things more likely, right? So it's more like I tried a bunch of stuff, I saw which things were good, and then I adjusted myself, I adjusted my own little brain to like make those good things more likely. But I'm never taking a gradient through the reward, and I'm never taking a gradient through the environment. So this is like a little bit counterintuitive, but policy gradient is never taking the gradient through the environment. Whereas model-based reinforcement learning, which we'll cover later, does take the gradient through the environment. Okay? So let's put these pieces together. We want to get the gradient of the objective. We saw that as grad log p theta tau times r tau in expectation, right? And we just did all of this mumbo jumbo to get that grad log p theta tau is the sum of the gradients of the policy. Yeah. And so now we can substitute that. And so this is going to be, remember there's like a bracket here. It's going to be the sum of grad log pi theta times the sum of the rewards, right? Taken in expectation over all trajectories. So you can think of this as you sample a trajectory, you sample an entire trajectory, you compute the grad log pi for every individual time step, right? Use PyTorch to compute it for every single time step. Then you sum up all of those gradients, and then you weight all of those gradients by the sum of the rewards in the whole trajectory, okay? So it's important, those brackets are important. I should really fix my slides. But essentially it's saying that you sum up the gradients for everything in the trajectory, and then you sum up the rewards for everything in the trajectory, and you multiply them, and then you average them over many, many, many trajectories to give you the gradient of the objective with respect to theta. Okay. And that'll give you a direction to move theta in. And now once you have that, then you can say theta is equal to, or theta prime is equal to theta plus alpha times this gradient, right? And so you're going to like essentially sample a bunch of stuff, compute this gradient, compute this reward, take a weighted sum, like a weighted average, right? And then you like get your gradient, and then you move your parameters in the direction of that gradient by a little bit, and then you have to recompute your sum. Yeah.
What is that T dash?
Oh, yeah. Okay, yeah. So that's a good question. So here what I'm saying is to compute the gradient at any point, for any theta, you're going to draw a bunch of samples from your current policy, right? So which means you're going to start from your initial state, take actions from your policy, run it in the environment. You're going to repeat this process, which is what you'd call a rollout, right? You run your policy in the environment. You get an entire trajectory. You get an entire trajectory, okay? And trajectory is a sequence of states, actions, rewards. States, actions, rewards, right? States, actions, rewards, till the end of the trajectory. Now, the way you're going to compute this, the reason I said these brackets are important is because it's not like a nested thing. Right now, it's just like you compute two separate things and you multiply them. Because you can think of this whole thing as this bracket, and then this whole thing as this bracket, right? So you compute these two things and multiply them. This thing is basically you take the gradient of the policy at every state and action, right? So this is going to be like, let's say your parameters were k dimensional. This is going to be like an rk vector, right? So there's going to be something of rk dimensions. You're going to sum it up over all the time steps. This thing is going to be a scalar, right? So this is going to be r1, right? And so then you're going to take this k dimensional thing, which is your gradient, sum it up over all of the time steps. You're going to take your scalar, you're just going to multiply them. K is the number of parameters, right? So like the gradient is parameter dimensional, right? So K is number of parameters. So it's like the dimension of theta. Okay. So this is the dimension of theta. You sum it up, you take a scalar, you multiply those, and then you compute this for every single trajectory. And then you average it over all the trajectories. Okay. The next typesetting will write that out. You have a question, Yohan?
So I guess like the way, if you can practice that, way, you're basically saying like the reward is computed for the trajectory, not like every time step.
That's right. And the reason for that is because the time steps are not independent. right? So it's like how good my action is. It's not just how good my reward was, it's how good everything else was in the trajectory. And we'll find a way to make it a bit better than this. But right now what's happening is it's saying, look at how good my trajectory was. For good trajectories, upweight everything in the trajectory. For bad trajectories, downweight everything in the trajectory. So they're all coupled because your outcomes are not defined by yourself. They're only defined in the context of the whole trajectory because it's a sequential process.
Was the very first like initial policy just random?
Yeah. Yeah, you initialize it with like Xavier in it or something. You just like have some random neural net. But it's a great question because often the choice of initialization really matters. Especially in the maze example I was giving earlier. Like if you're just doing random stuff and your reward is like at the end of the maze, it's unlikely you'll get it. And so often choosing good initializations or like initializing from another process can help a lot in practice. Okay. Does this make sense? So what we've done is we've sampled a bunch of trajectories for each of them, computed the sum of grad log pi's, weighted them by the sum of rewards, multiplied those whole things. We're going to get some RK dimensional thing. You're going to average it over many trajectories. You're going to get an RK dimensional output, which is a gradient, right? And then you'll take a step on the parameters. Yes? Okay, so we can typeset that better. Oh no, happened again. We can typeset that better. And so what we're going to do is, this is an expectation. Expectations are still not computationally computable. Let's write it as a bunch of samples, right? So an expectation is approximated by a number of samples, where n is your batch size, right? And so what you're going to do is you're going to sample n different trajectories. For each of the trajectories, you're going to compute the sum of grad log pi. And then you're going to compute the sum of rewards in that trajectory. You're going to multiply those things and you're going to average it over n. Right? And so each of these things is now computable. Like you're going to generate a bunch of samples. You can compute each of these with auto differentiation. This is coming from your rewards. Like every term is computable. Right? Okay. Does that make sense overall? Like the intuition here is maybe easiest understood here. I'm gonna reshare that. Okay, good. And so the intuition is easiest understood here, where you're saying, I'm going to sample a bunch of trajectories. Some of those trajectories had reward 100, some of them had 30, some of them had -10. The trajectories that had reward 100, and when I say reward, I mean like the sum of rewards in that trajectory was 100. I'm going to take all of the actions in that trajectory, upweight them. And things that had reward -10, all of the trajectories, all of the actions in that trajectory, I'm going to downweight. And then 30, I'm going to like upweight a little bit. Okay? And so the point here is you're going to move things up and down according to the reward. Yes? Just like trial and error, try a bunch of stuff, good things more, bad things less. That's it. And the reason you have a gradient is because you're trying to move the parameters of your policy in a direction that upweights things that are higher reward. Okay. Everyone with me for policy gradient? Does that make sense? Okay, so the overall algorithm is what we just said. We're going to compute this gradient as we just defined. We're going to essentially collect a big batch of data. So you're going to sample a bunch. You're going to compute the gradient by computing this average that we have up there, right? And then you're going to take a single step on the policy, but you have to collect data again. So it's really important in policy gradient to collect data again. Why is that?
Because your policy changed.
Because your policy changed, right? And so your gradient here, maybe best understood here, your gradient depends on sampling from your current policy by data. If your policy changed, that gradient is no longer valid, right? Even if you say, I'm going to keep the samples around, I'm just going to take the grad log pi's, that's a wrong objective because this gradient needs this to be from pi and needs this to be from pi, right? And so the reason policy gradient is called an on-policy algorithm is because every time you need to take a gradient step, you have to collect a bunch of samples from the current policy, right? And so that means that every time I need to go through this loop, I have to collect data, compute the gradient, change my parameters, and collect data again. Okay? So the reason this is expensive is essentially all of my previous data is not useful. And there's like ways to make it more useful, and that we'll cover that in off-policy RL. which is next week. But right now, what's going to happen is you're going to take your data, you're going to take a step, and you're going to throw all your data away. You're going to literally throw it away. And so you only use your latest batch of data. Does that make sense? The gradient depends on sampling from pi theta, your current pi theta. So you can't use old stuff. Okay, so this is what makes policy gradient really expensive, along with the variance issues we'll discuss. But part of the issue is you cannot use any old data. You can only use the latest data. And so the algorithm is going to be, you sample a bunch of trajectories from the policy, you compute your gradient, and then you take a step on your policy parameters, you sample again, you recompute the gradient you do. Right? That's what makes it on policy. Yes? So if you guys had to magically fix this on policy problem, how do you do it? Just as a precursor to next week. Like, what are ideas for like reusing this data? Learn a model from the data you generated. That's perfect. Yeah. So rather than having to, like, you'd still have to generate data, but that would be in imagination and not in the real world. That's a great idea. So that's what we'll call model-based RL, and that's why it's off policy inherently. What are other ideas we can do to make this, to resolve this problem? Yeah. In some sense, we're already trying to do that. The problem is that which things improve the reward is coupled with how you act in the future, right? So it's like, okay, I like acted this way. I want to act in ways that improve the reward, but that's inherently coupled to all the ways that I act in the future, right? And that is under my current policy. So that's what makes it a little tricky.
What if I take a very small step so that my past data is still valid?
Yeah. So what we're going to do is something that looks like that, taking a really small step, and then what you're going to do is you're going to like approximate this objective by like faking that this came from, even though you need to take it from your latest policy, if your policy is not too far away, you can fake that it came from the old policy, and it's not so bad. And it's a lot of the methods that are more efficient to basically do exactly. Okay. Yeah.
Would it make sense to, right now you're sort of lumping all the time steps together?
Yep.
Instead of that, what if you have gradient for each step multiplied by reward? So let's assume that you have a dense reward, not sparse reward, but assuming you have a dense reward, you could do that.
But when you've gone to a dense reward, in some sense, you've reduced it to a one-step problem.
Yes.
And so in that sense, yes, but I think the general framework can't assume that. But yes, for sure, if it basically you've reduced the effective horizon to 1, and then that works. Okay, but these are all great, and we'll yes, sir?
So
Yes.
So like here, it says run it on the robot, so like this assumes no simulator, like you do.
So by robot, we just mean whatever environment you're trying to run, right? So it could be real, it could be sim, doesn't matter. Like the way that most RL algorithms work in sim is like essentially treating them like real. So it like, this is just run on the environment, whichever environment. Good question. Okay. So we'll cover lots of strategies to kind of deal with this problem, but it is a problem, right? So let's kind of like try to instantiate this even more concretely. So how is this connected to supervised learning, right? So supervised learning kind of looks like this. Let's say you had some sort of classification problem, right? So you have X and Y coming from your data set. X is your input, Y is your label, right? And you try to maximize the likelihood of the label given the input. That's what supervised learning tries to do. That's what behavior cloning did. You can essentially approximate that expectation by saying, if I had a bunch of X and Y samples, I compute the grad log P, I average them, right? And that gives me my gradient. And I don't have to recollect my data ever. I just compute that gradient, I take a step, I recompute the gradient, I take a step, I recompute, I take a step, right? And so that's going to be supervised learning. Now what reinforcement learning is going to do, it looks kind of similar, right? But it's going to be a little different. And so it's going to be, you compute your grad log P's kind of similarly. You're going to weight them by your rewards. But you're going to have to continuously do this by collecting more and more new data, right? So the difference here is that you collect data once, and you just have to recompute the gradient over and over. The difference here is that, okay, it's kind of like weighted supervised learning. If you look at the objective, it's like grad log phi multiplied by some weighted rewards, like weighted supervised learning. But the important thing is that the data has to continuously be resampled. So unlike that, it looks similar, but it's a little bit misleading in that this expectation needs the data to come from the latest distribution all the time. Okay. Yes? Okay, good. So how do we implement this? Well, what we're going to do is we're going to take our objective, right, which is going to be the average of sum of grad log pi times sum of reward. I really have to fix these brackets. Oof. But sum of grad log pi times sum of rewards, right? That's our expectation. We're going to compute the gradients. You're not going to write it by hand, even though you could if you wanted to, but you're just going to compute them with autodiff. So you're just going to do, torch dot backward, or loss dot backward, whatever. And then you're just going to compute your sum of rewards with numpy, right? And so essentially the way you're going to implement this is just using PyTorch or JAX or whatever your favorite framework is. But an easy way to think about this is to start from maximum likelihood of supervised learning. Supervised learning is going to say, given some states and actions, right? Let's say this is what behavior cloning is going to do. You're going to like send your states forward through your policy. So this is for a discrete action space. So you're going to send your states forward through a policy, right? This is going to compute the likelihood of the actions under the distribution that you get from the policy. So like this is saying get the distribution pi theta of S, right? So if it's a categorical distribution, it's going to be, you have your neural net, it's going to take an S, it's going to output a vector, right? Vector is going to be a distribution of unnormalized probabilities. And then like one for every action. So if you have like n actions in your discrete space, you're going to have one for every action. And then the next thing is going to try and say, find the log likelihood of a particular action that you actually took, right? So let's say you took action 3. You're going to find the like log likelihood. The reason you have to do this cross entropy thing is because it's like unnormalized. But essentially it's saying find the log likelihood of the third entry in what the policy predicts, because that's what it actually took. And then you're going to try and like minimize the negative log likelihood or maximize the log likelihood. You're going to say, this is going to give me my policy distribution. This is going to compute the likelihood of the action that was actually taken. And then I'm going to try and minimize the negative log likelihood or maximize the likelihood. And then I'm going to take a gradient, right? So this is a supervised learning loop saying, get the likelihoods, minimize negative log likelihood, take a step. Yes? I'm not going to go through this too much. The PyTorch tutorial today should go over it for those who are not as familiar. But intuitively, all that changes here for reinforcement learning is you're going to do exactly the same 2 steps that we did before. You're now just going to compute like our Q values. Let's call them Q values for now, but they're essentially the sum of rewards in your trajectory. You're going to take your log likelihoods. You're just going to multiply them by your sum of rewards. And you're going to use all the same objective, right? And this whole thing is going to be in the loop where you keep recollecting the data. But in the inside the gradient step, all that changes is you just multiply it by the sum of rewards. That's it. So it's supervised learning weighted by the sum of rewards with the data collected over and over and over. Yeah.
It's kind of go back to quantitative distribution, you can, I guess, apply.
You don't have to assume that rewards are additive. There's some nice things about rewards being additive in that you can like use the Markov property. So for instance, if rewards are additive, I don't have to like worry about, like I can just like worry about rewards only in the future because I can just subtract out rewards in the past. And so there's like some nice properties of addition that allow you to enforce things like the Markov property, whereas if you just had a joint thing across all of the states, let's say you just had a big function that takes in trajectory, gives you a reward. It's hard to do like time-specific slicing of that reward. And so what we're going to do next is we're going to show that we can like make this more efficient by only considering rewards in the future And it's hard to do that for non-additive rewards. You could do it for multiplicative rewards too, but it's just like the formula is in the feature. You could probably rederive most of this for multiplicative rewards too. Okay. Does it make sense overall? Yes. Good. So the way we're going to try, let me instantiate this even more concretely for a Gaussian, right? So let's say you had a Gaussian pi of A given S, where the S is going to go into a neural net and it's going to give you mu theta and sigma theta, right? And so it's basically, you can think of this as a neural net that takes an S and outputs two vectors. One of them is going to be the mean. And so let's say you have a k-dimensional action space, it's going to be a k-dimensional vector for the mean. And then it's going to output the log covariance. And so the reason you want the log covariance is because covariance has to be positive semi-definite, and it's hard to get a neural net to obey that. And so if you have the log covariance, you can take the exponent afterwards to get the covariance. And so usually the way you're going to parameterize these things is you'll have something that takes in a state, gives you a mean and a log covariance, and you like convert that into the covariance afterwards. But essentially, what's going to happen is my log likelihood given some mu theta, which depends on theta, the parameters of the policy, and sigma theta can be written as something like this, right? They're just the Gaussian likelihood. But the important thing is that S is going into this thing is theta, it outputs a mu, it outputs the log covariance. And so like this whole likelihood is directly a function of theta, right? So which means I can compute the gradient of this likelihood. And so what I'm going to essentially do is I'm going to take like log of this function and then run it through PyTorch autodiff. And that's going to give me the gradients of this log likelihood with respect to the policy parameters, right? So all you really need to do, you don't have to do this yourself, like use torch.distributions, and torch.distributions will give you the gradients with respect to theta. So all you need to do is take those gradients, multiply by rewards, and you're done. Yes, should be super easy. Good. So does it work? Kind of. Here's some examples I got from CleanRL from things that are based on policy gradient. So this is not literally policy gradient. The version that we've talked about so far is kind of like that version. But hopefully we'll build up to the version that's on the top, which is something that looks like PPO. And it does work in practice, but not this version. This version is just the starting point. Okay. PPO, yeah. It's called proximal policy optimization. We'll build up to it as the last algorithm will cover. But it's basically like this thing with a bunch of tricks on top. Okay, that's policy gradient. How do we feel about it? Yes? Confident? We can release homework 2 today, along with homework 1. Okay, so the next thing we want to cover is why is policy gradient challenging? So we've talked about it a little bit. Yeah, why do we think policy gradient is hard? Like why I said that the policy gradient is like this horrible line on the bottom, right? Why is that? What makes it hard? Yeah. Throw away all your past data. Exactly. What else might make it hard? Yeah.
First base sum over all the rewards and all the actions.
Exactly. Sum of. Right. Exactly. Yeah, exactly. So you're like lumping things together, right? And really the key is that it's hard to tell what matters without looking at lots of samples. In other words, it's called a variance. But essentially what you're doing here, if you look at this objective, right? You're taking a single trajectory. You're summing up the grad log pi's along that trajectory. And then you're summing up the rewards along that single trajectory, right? You're saying that like, okay, your policy was stochastic, your dynamics were stochastic. And really what you're doing is you're just accepting all that stochasticity and saying, I'm going to like just take the sum of reward along my trajectory, right? And this is what you'd call a single sample estimate, because it's saying, I'm going to weight this not by some average over many trajectories. I'm going to weight this just by the single sample trajectory that I saw, right? And so really what you want to do is be something closer to, do I have this? Yeah. you want to be closer to something that looks like this, right? You want to say, from this state in action, there's many possible futures. I want to like average them, so I like remove the effects of stochasticity, right? But if I just take a single sample estimate, like we did here, what's going to happen is I'm going to accept all the effects of stochasticity. I'm going to take all my actions lumped together. I'm going to like couple together lots of things, which means that to like disentangle whether a single action was good or not, I need a shit ton of samples, right? And that's what the issue of variance. Basically, you can think of variance as like the number of samples that you need to bring the accuracy of the estimator to like what you need it to be, right? And so like essentially what's gonna happen is if I draw some set of samples and n is pretty small, then the gradient is going to point one way. And if I draw a different set of samples and n is pretty small, the gradient is going to point another way. Right? So if you like draw independent samples, the gradient is going to like be super noisy. And so essentially your parameters are like moved by this like extremely noisy gradient, which is high variance. Right? And so what most policy gradient methods have to do to deal with this is like blow up n. Right? So you like blow up n, and if n is big enough, then you like average out all these stochasticity effects, but then you have to like have huge n. So if you see any of these like PPO curves, and you see like, let's see if I have them on here. That's like 1 million samples. And this thing is at -500, right? And so it takes in the order of 10 to 20 million samples to do anything, because every time you do an update, it's so many samples because the n has to flow in. Right? And so variance matters because variance is directly connected to sample efficiency. It's like how efficient is your algorithm? And sample efficiency matters because running your robots is expensive. Right? Okay, so essentially, the issue is that you're taking a single sample estimate. You're only weighting things by like the sum of rewards in your current trajectory. Right? And so some things are important here. As you were saying, couples together all the actions, right? That's an issue. The second thing that's a problem is that if different trajectories have different reward scales, depending on which ones you sample at any point, the gradient might look pretty different. So it's pretty susceptible to variations in scale. And lastly, if you have like lucky samples, let's say you're in a stochastic environment and you like accidentally like chance upon something that's good, in a single sample estimate, it's going to believe that that is actually a really good course of action, even if it wasn't, right? And so you're like really susceptible to lucky outliers. And so the issue with policy gradient is like all of these things essentially sum to variance. All of these contribute to variance. And by variance is just different draws of the gradient with n being small are very different. You can check this empirically when you're running policy gradient, compute for the same policy parameters, compute the gradient 10 times and just like look at the cosine similarity of the gradient, you'll see that it's super different. Unless you blow up n to be ginormous. Okay, so maybe you should add that to the homework. Okay, does that make sense? Yeah.
Sorry, what do you mean by scalarity?
Like imagine that there was some states that were like had reward 100 and some states that had reward -100. But like inherently one of the states was like just a lower reward state and the other was a higher reward state, but both of them are contributing to the gradient. And so like they're going to be weighted super differently. So what you care about is like at a state, which action is good. But if a state is inherently at -100, another state is at +100, you don't want their effect on the gradient to be extremely different because then it really matters which states are in your batch for an update. And so we'll cover that in more detail so it has more context. But essentially, intuitively, it's like different states have different scales and they're all contributing to the same gradient. And so that might change your gradient. Okay, so what we really want is to go from this high variance single sample estimator to something that looks more like this. Something that looks more like this, where you're like really able to say for the same state and action, I took many possible futures, and then I like computed what the average effects were in the future, right? And then if I compute the average effects from the same state and action, then I'm golden because I like have removed all the variance away, right? Now, why can't I do that? Why is it hard to do this? Exactly, right? So you're in a continuous environment, which is like a measure zero set. which means you'll never be back in the same state. And you're not, like in the real world, you can't reset to exactly the same state. And so you'll never be able to take repeated actions from the same place. And so really what you end up with is something that looks much more like this than something that looks like what we want, which is this. Okay. Yeah. It's like the likelihood of you ending up in exactly the same state is close to zero. Okay. So if you're in a simulator, you should do things that look more like this. You should reset to the states. You should compute lower variance estimates, and people don't, and they should. But if you're not in a simulator, then you have no option, right? Okay. So the fundamental problem of policy gradient is one, it doesn't reuse past samples, and two is that it has high variance, right? And so we'll cover the fact that it doesn't use past samples next week, and we'll try to deal with variance today. Yeah. Okay. So let's start with the first one, the first issue, right? Remind me of your name. Okay, so you're saying that it couples together all the actions, right? Let's try to deal with that issue first, right? So the first issue that if you look at the objective here, the first thing we noticed is that, hey, we took together all of these grad logs and we multiplied it by the reward of the entire trajectory, right? But like, that seems crazy because you're like tying the outcomes of one step to all of the other steps, right? And you don't necessarily need to. And so the first thing we're going to do is we're going to try and like unhitch the outcome of a single step from all of the steps in the trajectory. And you can't do that willy-nilly, like I was just telling you on. Like you're in a sequential decision-making process. So your actions do affect things in the future, but they don't affect things in the past, right? And so the first thing we're going to do is that notice that trajectory returns naturally have a causal nature, right? So it's like the actions that I can take now will only affect what will happen in the future, never what will happen in the past, right? And so what it says is that right now we're saying we're going to sum up rewards for all time steps going forward. Or we're going to sum up all time steps from the start, and then we're going to weight every log probability by rewards for everything in the trajectory, which means that even if I have a grad log pi here, it's like getting weights from rewards here, right? Which is saying that like, why does that matter? Grad log pi at that time step cannot possibly affect what happened in the past, right? Your Markov land. And so it doesn't possibly affect what happened in the past. So why am I considering rewards in the past, right? And so all we're going to do is we're going to go from the notion of summing up all rewards to only summing up rewards in the future, right? And so we're going to say, we don't want to include any t primes which are less than a particular t. So we're going to try and convert this to only, this is like a little subtle, but you're going from 0 to t here. Here you're going from small t to capital T, right? And so now this is not, earlier here we had the brackets like this. Here what you're going to do is the brackets are like nested, right? So the brackets are nested, which means that for every time step, I'm only going to consider the sum of rewards in the future, right? And so the way you can think about this is that I'm going to go through a trajectory. For this time step, I have to consider all the rewards in the future. So I'm going to take grad log pi of a naught given s naught, weighted by the sum of all rewards in the future, right? So from t equal to 0 to capital T. The next one, I don't actually care about this guy anymore, right? So the next one, I'm going to take grad log pi a1 given s1, and then sum up rewards from t equal to 1 to capital T, right? And then the next one, I'm going to take grad log pi a2 given s2 and sum up rewards from 2 to capital T, right? And so the point is that you don't, if you're at this state because you're Markovian, you like cannot affect the past. The past is the past, right? You're saying that what is the best action to take from where you are right now? And the best action to take from where you are right now, it does affect the future, but it doesn't affect the past. And so all we're going to do is we're going to change this thing, which first summed up all the grad logs and all the rewards. So for each grad log, you're only going to consider the sum of rewards within the future, right? So you can think of this as like each grad log is multiplied by the sum of all rewards, and then all of those are summed up. Here, you're gonna say each grad log is summed up, is multiplied by the rewards only in the future, and then they're all summed up. Right? And so the important thing here is the bracketing. Jacob, are you here?
Yeah.
Can you make a note for us to fix this in the slides? Just it'll help people with homework and stuff. Yeah, go ahead.
So earlier, all the time steps were kind of weighted equally. So you
Yeah.
have the same reward,
Yeah.
but now later ones kind of have more reward weighting than later ones. So do we leave it like that, or do you divide like the reward by how many times stuff it comes?
You don't do any renormalization. Normally, you'll do this with discounting. And so like you'll have like a gamma to the whatever t here. But besides that, you don't do any reweighting because it's like the way that the environment is set up, like how good the last time step is affects the futures of all of the states. So it should actually affect everything. Whereas how good the first thing is kind of doesn't affect anything after that. Or like when I'm at a state, I like cannot change the past. And that is true for everything. That's true for everything after the first step. Yeah. Good question. Okay, so all we did is we changed the bracketing. You can actually show that this objective is equal to this objective. If you go to the integral version, you can show that if you can use the Markov property to show that basically the terms, I basically cut out a bunch of terms to go from here to here, like everything that is in the past. You can show that those terms basically sum up to 0 because you cannot affect the past. And so, yeah, that could be some exercise for home. But yeah, intuitively, all we're doing is we're just saying only consider things in the future. Right? So that's what you call return to go. Right? And we just want to weight things by return to go. Okay. Does that make sense? All we used is causality. We just converted this thing from t equal to 0 to t equal to t to capital T. Sweet. The next thing we're going to study is the susceptibility to scale variations, right? Thing I was just talking about. So here's an example I stole from my PhD advisor. But basically, it's a plot of trajectories on the x-axis, and it's overloading probabilities and rewards on the y-axis. Okay? So we're going to say these are different trajectories on the x-axis, and we're going to have the rewards be these bar lines, and we're going to have their probability be this curve, right? And so I'm just going to do a little bit of overloading here, but essentially these are different trajectories. Under your policy, they have this likelihood, right? And under your environment, they have this reward. Does that make sense as a setup? Right. So what we want to study is for these 3 trajectories. If I sample 3 trajectories, they got reward this, this, and this. How is the likelihood under my policy going to change with the policy gradient? Right. So this was like, you can think of this thing as p theta tau. You can think of these thingies as r tau. Okay. And we want to see how does the policy distribution change with this sampling of r tau. Right. Okay, so if this was your if this was the rewards that you got, how is the trajectory distribution going to change? Shifts to the right. Okay, so shifts to the right. So basically this thing is like super negative, and you really, really want to avoid this thing, right? And so you're just going to say, I just want to go as much to the right as possible, right? So essentially saying these things are a little bit positive, but this thing is really negative, and I really want to avoid that. And so you'll get a shifting to the right. Yes. Now, if I'm taking the gradient of an objective and I just added a scalar to the objective, the gradient shouldn't change, right? Just scale it. So what I'm going to do next is I'm going to like add a constant to them, right? So all of those rewards are higher now. So it's the same relative distance. I just added a constant to all of them. And so now how is the reward? So this is the same, it's the same MDP, if you will. I've just added a constant reward. So how is the policy going to change now?
It'll shift to the right still, but maybe less.
Yes, exactly. It'll shift to the right still, but maybe less, because it's saying, well, push up this guy, but push up these guys more. right? So saying, okay, push this guy up a little bit, push these guys up more. And so it's going to be less of like, deadly avoid this thing and more of like, push the right up a little more than the left, right? And so for two things that should have been the same, we got like pretty different changes in our policy distribution, right? And the problem here is that if I have different states, let's say, which have different scales of rewards, what's going to happen is that the gradients that they yield, even if there's just a constant shift in reward, is going to be super different. Right? And what you really care about is not what the absolute value of the reward is, but you care about like how some actions are better than other actions. Right? So you care about that if I'm at some state, I took action A1, A2, A3, and if A2 was the best, I want to take more of A2, but relative to A1 and A3, right? Or if I'm at some other state and I took like different actions, and A1 was the best, I want to take it relative to the like value of the actions at S prime, right? Not at S. And so what's going to happen is that you have two different states which have pretty different rewards. You're going to have different magnitude of the gradient and a different value of the gradient, unless I take a shit ton of samples, right? So this goes away if I take like a ton of samples because the gradient becomes like smoothed out. But if I have small numbers of samples, this like variation in scale is going to cause a big issue because it's going to like yield different gradients. Right. So I spent a bunch of time looking into this yesterday. I don't think anyone on the internet has a great explanation, but I think the two explanations of this that I find the most intuitive are, one is that if you have different states with different scales, the gradient magnitudes are going to be different, and that's going to be different depending on which states show up in your batch. Another way of thinking about it is that if you like added a constant to things, like the range of your values are larger, and if the range of the values are larger, your variance grows, right? So if you scale a random variable by some amount, the variance grows. But the way I find it to be most intuitive is to just look at the difference between this, right? And if you add a constant to it, you see that the gradient is different, and it shouldn't be, right? How do we fix that? Different states, different scales lead to different gradients. How do I fix that? Yeah. Normalize, right? Yeah. Essentially, what we're going to do is we're going to try and center them, right? So what we're going to try and do is at every state, we're going to try and subtract something from the rewards so that you center them as much as you can, right? So you like, let's say you subtracted the average reward, right? And the average reward at every state, you're going to subtract from the value. What's going to happen then is like the reward distribution is going to get centered across every state. And that's going to like reduce a lot of this variance. And so you can kind of think of it as earlier, we were dealing with some situations where some things are being pushed up, some things are being pushed down. And in this case, everything is being pushed up. And so instead, what we're going to do is we're going to just center everything to be centered around 0, let's say. And that's going to like reduce the scale variations across states because every state is going to have it be kind of centered around the average. Right. So now you're never going to have this versus this. You're always going to have like some version of this for all the states. Does that make sense?
I had a question regarding the initial idea. Having something like super negative or like the values.
Yeah.
Versus the new graph.
Yeah.
Because if the absolute like value difference between the two values are the same.
Yeah.
Then what part of our, I guess, equation is causing the preference of avoiding negative values over?
I think the reason it's happening is because if you had like a expectation that you were like if you had an expectation where you had infinitely many samples, like this would not be a problem. Like if I had infinitely many samples that were all following this distribution and infinitely many samples over there, then these two things would be the same. It's when I just have a small number of samples, that's when like if you like write out the analytical solution for both of these things with just 3 samples, you'll see that they're like the shift will be different for for that case and this case. So the thing that's causing it is the fact that we're approximating our expectation with just a small number of samples. So the expectation remains the same with infinite samples. Okay. So what I'm going to suggest is that we are going to take our objective from earlier, right? The one where we said we're only going to consider rewards in the future. And so it's going to be grad log by times sum of rewards in the future. And we're going to subtract this thing we're going to call a baseline from it. And so baseline is what we're going to call B. B is a function that only depends on the current state, right? So notice that the bracketing here is important. The baseline does not depend on anything in the future. Your baseline only depends on the current state, right? And it does not depend on the action. So it's important that it doesn't depend on the action. It's important that it doesn't depend on states in the future. And so essentially what you're doing is you're saying this is your sum of rewards in the future. This is kind of like our average reward. We're going to subtract it, and we're going to say that's going to like center the rewards or the returns, and that's going to reduce variance. And I'll prove why it's okay to do that.
You said that adding scalar to rewards changes the.
Yeah.
Like if you change the means of the segments very normal, how does that change the means?
So it's like if you I guess it's to provide intuition, but I think if you scale a random variable, then you change. Yeah, but you're right. If you just add something to the random variable, it doesn't change variance. Yeah. So okay. So we're gonna try and subtract this term B of ST from our sum of rewards. Notice that there's no action dependence and no future state dependence. It only depends on the current state, right? So you're going to say for every time step, I'm going to take grad log by, multiplied by sum of rewards, and subtract a function that only depends on the current state. Okay? And that's going to be our baseline. And we're going to argue that this is okay to do. It doesn't change the objective. So we're going to argue that basically it's going to be an unbiased estimator, which means that this expectation, this thing is going to be the same as your original objective, but it's going to be lower variance. Yeah. So I mean, I did something kind of arbitrary, right? I subtracted some random number from the right-hand side. Like we need to show that it's the same objective, right? Otherwise, this is not a valid thing to do. Okay, everyone with me so far? All we did is we took our sum, we made two changes to the policy grid. The first is we ignored things in the past. And the second is that we subtracted this function B of ST, which only depends on the current state. Right? And we argued that okay, the going to return to go rather than full return decouples you from things in the past. And the baseline is going to center things and reduce variance. Yeah.
Quick question. Why are we using this to normalize the rewards instead of doing something more conventional, like averaging the time by the
You do both often. You often do both. You often do both. Yeah. So in practice, what you'll do is you like subtract the baseline, and you will like average the returns. And so you can kind of think of this as like this thing is kind of like converting. It's converting something that looks like a sum of rewards into something we call an advantage, which says like how much better is taking this action than the average. And so this is kind of like, this is the average. This is like how good taking your current sequence of actions was. Right? And so this thing is telling me how much better is doing this than the average outcome. And then you'll often take this thing and then you'll normalize it. You like subtract by the mean, divide by the variance. And so you'll do both.
It's B learned.
B is learned, yeah. We'll talk about how we learn it in a second. But let me first tell you that it's okay to do it, and then I'll tell you how to learn it. Okay, so the next thing I want to prove is that if I subtract a B, it's not going to change my estimator. Right? So what I want to show is that I've taken this objective, I've subtracted some measure of SC from it. I want to show that like it doesn't change my estimator, which means that it's the same as if I didn't subtract the B of ST in expectation. Right? So the estimator is unbiased, but it's going to be lower variance. Right? So when I say unbiased, I mean in infinite samples, it gives me the same thing. or an expectation. Okay, so what I want to show is that this is my objective, right? So I've rewritten my objective. It's a little important what I did here. So I took my objective, which is essentially expectation of a trajectory of grad log of the grad log p theta tau r tau, right? That was my policy gradient. And I'm going to rewrite this in a slightly easier form to make our life easier, which is saying that let's sample states and actions according to the distribution of the policy. And so it's saying if I ran the policy in the environment, I'm going to get states and actions from that distribution. Then I'm going to like take the average of grad log pi theta at given st multiplied by sum of rewards in the future minus p of st, right? Something like that. So all I did is I like convert, if you remember my first lecture, we converted from trajectory form to stationary distribution form, right? But all we're doing is we're writing the same policy gradient objective. And what I want to show is that this thing is going to be equal to if I didn't have this term. So I'm going to show that this thing is going to be equivalent to grad log pi times the sum of rewards without the second term, right? So I just want to show that in expectation, those things are the same, which means that essentially what that means is that this term, if I like split up those things into two terms, I just want to show that this term over here is 0, right? If that term over here in expectation is 0, that means that this estimator is unbiased. It's the same as our original objective, right? And so all we're going to try and do is we're going to try and prove that this thing on the right is 0. Okay, so how are we going to do this? So let me recap why this matters. We did this thing to we subtracted b of st. We said this is going to reduce the variance, but I want to show that it's not an arbitrary thing to do. It actually doesn't change the expectation, right? So we're just going to try and show that the second term goes to 0. And by showing the second term goes to 0, we're going to show that this estimator is unbiased. Okay, so how are we going to do it? Right, so we're going to try and first decompose p of st, which is like the distribution of states and actions you get under your policy, as the distribution of states times the distribution of policy of like the distribution of the action given your state for your policy, right? So you can say p of st at is the likelihood that you got to a state times the likelihood you took the action at the state st, right? So that's going to be the first step. And our second step is going to be to like, this is going to be an integral over S. This is going to be an integral over A. So we're going to take out all the terms that don't depend on A outside of the first integral, right? And so we're going to say, okay, like this thing doesn't depend, and this thing doesn't depend on A, right? So they're going to go outside of your first integral. And so this is going to be an integral over S. This is going to be an integral over A. So you can kind of think of it this way, right? So you've taken this double integral, you've separated out the terms that don't depend on A outside. So the reason I said the baseline cannot depend on A is because if it depends on A, then you cannot take it outside, right? So it's really important that it doesn't depend on A. And so your baseline doesn't depend on A, you take it outside. And now I have this expression. Oh no. I have to read. No. I have to reshare again. Okay, so oh, it's still here. No, we're just gonna deal with it. Okay, so we've said we've taken all the things that don't depend on A outside, right? And now we have this expression. What I want to show is that this expression is equal to 0. So let's try to play around with it. How do I get this expression to be ideas? Yeah. It's want to show that it's equal to 0. Okay, how else can I show that sequence is equal?
Can we change the variable and do integration by parts? I think this is like x gradient of log x. And
We could do integration by parts, but I think there'll be something easier here. So like, what if we just did, let's just use the chain rule here, right? So if we use the chain rule here, this is going to be 1 over pi theta times grad pi theta, right? So that's just the chain rule. And now this is going to be pi theta times 1 over pi theta times grad pi theta dA, right? That's what this inner integral is going to become, right? We just use chain rule. And so now we can cancel these guys out, right? And now we're going to do the opposite of what we did for policy gradient. We move the gradient inside. Now we're just going to move the gradient outside, right? So we're going to say gradient or integral of gradient of pi theta. We're just going to move this all the way outside, right? So I'm just going to recap what we did. We said is we moved all the terms that didn't depend on A outside the first integral. Then we said we're going to use the chain rule on log pi. So we said we're going to say grad log pi is 1 over pi grad pi. These pi's are going to cancel. We're going to end up with integral grad pi dA, right? And we're going to move the gradient outside the integral again. We're going to move the gradient in or out, right? The same as we did before. The gradient's going to go outside, and I'm going to have gradient of integral pi theta dA. Okay, so now what is this then? So the probability distribution, so the integral is 1, which means the gradient is 0, right? And so this thing will be equal to 1. Now you have grad 1 equal to 0, right? And so now if you stick your 0 back in here, now you have integral 0, which is 0. So to recap, all we did is we separated the things that were not dependent on A out, and then we did the chain rule, and then we took the gradient back out. And then you have integral of a probability distribution, which is 1, and the gradient of 1, which is 0. And so why does this matter, right? Why did I go through all of this stuff? Why did I go through all of this stuff? Well, we wanted to show that basically, how do I go back to this? We wanted to show that like adding this B of ST term is not crazy, right? So what we did is we showed that if I take this B of ST term, I look at the expectation, the second term basically integrates out to 0. And if it's integrating out to 0, then it's in expectation unbiased, right? Which means it'll give you the same objective in expectation. But it'll be lower variance. Okay, does that make sense? So all we did is we made 2 changes. We like subtracted out this baseline, and we only depend on rewards in the future. And that's going to make it a lot better. So you can try this in your homework. Try not doing these things, and it'll make things a lot worse. Okay, good. So the question we had earlier about learning baselines, how do we get these baselines? There's like many different baselines you can choose. Some of them are good, some of them are bad. One that's often chosen is just trying to make the baseline equal to the average sum of rewards, right? And so this is what you often use in algorithms like PPO and like things used in practice. But essentially, you're trying to say, let me take the sum of rewards in the trajectory, right? And let me try and regress to the average sum of rewards. And so I'm going to, essentially what I'm going to do is I'm going to sample, I'm going to take a bunch of trajectories, right? And for each state in each trajectory, I'm going to compute the sum of rewards in the future from that state, right? So like for this state, let's call this S0. I'm going to compute the sum of rewards at all things in the future in that trajectory. For this state, I'm going to compute the sum of rewards for all things in the future in that trajectory, right? And then I'm going to have a data set of SI, and let's call this RI, which is like the sum of rewards in the future for that trajectory. And then I'm just going to try and regress from SI to RI. And if I regress from SI to RI, it's going to give me the average sum of rewards, and that's going to be our baseline, right? So this is what you call Monte Carlo regression, or just like trying to regress to the average. It's going to compute a bunch of SIs, RIs, SIs, RIs, SIs, RIs. You're going to try and regress from SI to RI, and that's going to give you the average. Okay, so essentially you're just going to get a data set of SI, RI from I equal to 1 to n, which is just a data set of all the states and future rewards, and regress from S to R. That's going to, and we often call this a value function, which we'll define more in detail, but for now, let's just call it P. Okay? And so what you're going to do is you're going to solve this regression problem. You're going to solve this regression problem. You're saying compute the sum of rewards, try to regress to it. And then you're just going to subtract that from your sum of rewards in policy gradient. Right? So policy gradient is going to compute the sum of rewards in the future in a single trajectory. Right? So the way you can think about it is you're going to like go through your trajectories. For each trajectory, for each state in every trajectory, you compute grad log pi. So let's say you had a trajectory. Let's say you had this state. You're going to compute grad log pi of AT given ST. You're then going to compute all the rewards in the future, the sum of rewards in the future. And then you're going to multiply it by the sum of rewards in the future minus your learned value function V. Like the important thing is that V can only depend on the current state, not on actions, not on states in the future. Okay, so if you do this, there's like people who've like come up with fancy methods to make it depend on actions and so on, but don't worry about it. The key here is that we're just gonna like subtract that out and learn it with just like regression. So you can just have V be a neural net, right? Yep.
So what we're doing here is we're just approximating the average.
That's right. That's right. That's it. You're just approximating with the average sum of rewards in the future. Okay, does that make sense? Yeah.
But we think that it's unbiased, that is good, so it doesn't change expectations.
Yeah.
How can we be sure that it actually reduces?
Yeah, that's a great question. So in the next slide, we talk about do baselines actually reduce variance. So you can actually show that the baseline, which is the average reward baseline, is not the optimal baseline. It's just it's the most convenient baseline. And it doesn't always reduce variance for every MVP, but it's often a practical choice. So the answer is you don't know. There's like an optimal baseline we can compute, but that's not the average reward baseline. Okay, how much time do we have? 5 minutes. Okay, we'll do this next time. But essentially, maybe I can just preview what we're going to do. We're just going to answer your question about like what baselines will reduce variance, and we'll try to like explicitly analyze the variance of that estimator, like actually get the variance, and then optimize it for the best possible baseline. And we like come up with a closed form solution for the best baseline. Okay, cool. All right, see you guys Monday. We should release homework tonight. You'll have 2 weeks or so to do it. Yeah, cool. Yeah. Yeah, you have my calendar? You don't have my calendar? Okay, feel free to ping me on Slack and we'll find that.
Okay.
Yeah, okay. Yeah.
What's up? Question about the here about this equation. I think you calculate the value function of each state, but since here you start from 1, so all the results is that it's all the
no,
same.
that's a mistake. That's a mistake.
To start from
That's
the-
correct. That's from the current time step P. Yeah. Let me write that down. That's very helpful. Thank you.